Hello everyone, it's me, Bill Younger again. I'm here to do an example 4 for the law of Biot-Savart. Now, the first three, if you watch them, were very rigorous, robust, and a little daunting for most people. But I've worked those out in great detail and explained all the details specifically so that we could get to this point where we can now easily apply the formulas and the principles we've learned in the previous three examples. So hopefully this will work out. Let me go ahead and share my iPad screen with you so we can see how one can use the Biot-Savart law uh, in a stepwise way without having to do all the complexities of all the integration and stuff of that sort, but still using the physical principles. So let me share my screen. So you can see here I have a statement that says use the Biot law to calculate the magnetic field at the origin of the diagram. So in this case, I actually already included the coordinate system. Obviously, this would be the most obvious coordinate system to use, specifically because it allows the k-hat direction and both the positive and the negative k-hat directions into and out of the page as the potential directions for the magnetic field at the point P, as a result of the three separate arcs that we're doing. Uh, and we just have to use the right hand rule to figure out which ones of those are plus or minus. And it's actually the point P is the center of curvature for all three of the arcs: the arc of radius R0, the arc of radius capital R0, and the arc of radius capital R1. And we're going to go ahead and solve it as follows. Normally, we would use the solution and say that the solution is Biot-Savart equation, but we're actually not using that this time. We did say earlier that the magnetic field magnitude for a circle was mu 0 I over, and then you could write it as 4 pi r times 2 pi, and then it's just a matter of using the right hand rule to decide in which direction it points, and what radius we have to have for each particular arc allows us to figure out the magnitude in each case, and then we just add all of them up, assuming that they all have the same center of curvature. I think a better way might be to write it like this. We can say if you have an arc or a segment of an arc, let's say, of radius r, and that was not very good. Segment of an arc like that, this angle will be delta theta, and that will be measured in radians. I'm going to say the actual current will be parallel to that arc, but pointing in that direction. The center of curvature, of course, is this point P, and when we have that, what we'd say is B is equal to, and we could actually put it in vector form by writing plus or minus mu 0 I over 2r. Now this time I'm going to write delta theta, which is supposed to be measured in radians, over 2 pi. And then I'll say out of page. So this quantity right here in these parentheses would be a unit vector out of the page or in the page. So I will actually do this with a red arrow. Now, in most cases, you can make your coordinate system so that this unit vector that sticks into or out of the page, you can make it into k-hat, and that is fine. It could also point into the page, and that could be k-hat. It doesn't really matter. The main thing is you have to be able to assign the actual appropriate direction for each particular arc. So this is another version that you can use. Feel free to use it. Again, it's B vector equals plus or minus mu 0 over 2r times parentheses delta theta over 2 pi, and you can see how that's exactly equivalent to the formula above it, but all of that times a unit vector that sticks out of the page. And I could have written a unit vector that sticks in the page. It doesn't really matter because we have the plus or minus that and covers both into and out of the page. Obviously, the plus with the word out of page meaning positive would correspond to a vector out of the page, and negative would correspond to a vector into the page. So now we're going to use that principle to actually compute what the magnetic field is at point P, which is at the origin. Now, the other thing we learned, especially in example 3, we learned that the little sections of straight wire that are aimed either directly towards the point at which we wish to know the magnetic field are directly away from the point at which we wish to know the magnetic field. All of those little current segments do not contribute any magnetic field to the point P. So that means this little section right here contributes nothing. This little section right here contributes nothing. This little section right here contributes nothing. And we just get a contribution from this one, a contribution from this one, and a contribution from this arc. So it's just a matter of computing all of that. And the easiest way to do that is as I'm showing you now. I'm going to say B at the origin, which actually I think I'll just label the origin, that O with a line on it like that. I'm going to say B is equal to, now what I have to do in each case is notice I have a mu 0 I and a 2 in the bottom for all of the terms. So I'm going to go ahead and write mu 0 I over 2 because that's going to be common to all of the terms. Now I'm going to use my right-hand rule to attack each segment. And specifically, I only care about this section, or this segment 1, this segment 2, and then this segment 3, because as I said, this radial line, which actually heads straight towards the point in question, means that dl cross rdl is 0, and this section, which heads straight away from the point in question, has dl cross rdl equal to 0, and this section, which points directly away from the point in question, has dl cross cross RDL equal to 0 as well. So all of those contribute 0, and specifically the RP in this case from the Biot-Savart law is 0 here because RP is supposed to be the point, or excuse me, is supposed to be the vector that leads from the origin to the point in question. In this case, the origin is the point in question, so RP is the 0 vector. So that's why me saying dl cross rdl is 0 is sufficient. Otherwise, it wouldn't be sufficient because the Biot-Savart law is dl cross parenthesis RP minus RDL. So we're going to do that. Now I'm going to use the right-hand rule because I realize that X and Y, being a right-handed coordinate system, dictates that I take my right hand, stick my right index finger in the direction of the positive x-axis, take my middle finger and stick it in the direction of positive y-axis, which is straight up, and then the z-axis would be the direction of my thumb, which is pointing out of the page. So k hat points out of the page. And now if I use my right-hand rule on the arc section 1, you'll see that grabbing that wire with my thumb going up and to the right, my fingers of my right hand are going into the page at P. Therefore, they would be in the negative k hat direction, as well as for for arc section 2, if I grab my that section of wire with my right thumb pointing down and to the right, my fingers go through the middle at P into the page. And then if I grab a section of arc on arc 3, let's say in this area, then my thumb pointing up and to the right, up and to the left, has my fingers of my right hand coming out of the page. So that, in fact, is going to be in the positive k hat direction. So I'm going to go ahead and put k hat for all of these because all of them are either plus or minus k hat. So the mu 0 I over 2 also has a k hat in it, and I'm going to put that in now. Now it's just a matter of putting in brackets. And since I like to have my positive stuff before my negative stuff, I'm actually going to take arc 3 first. And what I'm going to have is delta theta over 2 pi. And this is for arc 3. And then I need also, of course, the radius, which would be R1. That's going to be the contribution that arc 3 will make once I substitute delta theta in there. So what I'm really doing is taking delta theta over 2 pi, and then of course R1 on the bottom, and all of that's for arc 3. So now that I've sort of explained that in symbols, I'm going to go ahead and write out what that is. That is going to be delta theta, which obviously in this case, delta theta is a whole pi radians, 180 degrees basically. So I get pi over 2 pi, and now the radius of that particular arc is R1. And as I said, this is in the positive k hat direction, so that's why I started with that one. Now I'm going to go back to arc 1, and for arc 1, we know that's going to be a negative, so I'll put a negative sign there. That's going to account for it going into the page instead of out of the page. And the actual arc there is an angle of pi over 2, so I'm going to write pi over 2 divided by 2 pi, and then that radius is little r0. And then I'm going to do the same thing for arc 2, which is again pi over 2. Of course, it's also negative, and it'll be over 2 pi times capital R0. So now I've got basically the entire thing worked out. I can write mu 0 I over 2 times k hat. Now I can cancel out all these pi's. That pi cancels out with that pi, that pi cancels out with that pi, and that pi cancels out with that pi. And what we see is we get 1 over 2 R1. And what we get for this next one is 1 minus 1 over 4 little r0. And what we get for the next one is 1 over 4 big R0. And that's basically it. That's the whole answer. If we wish to make it a little more neat, we could possibly distribute through everything. I think that doesn't necessarily make it any neater, but just for completeness, let me go ahead and do that. Now I'm going to go ahead and distribute everything. What I'm going to get is mu 0 I over 4 capital R1 minus mu 0 I. By the way, yeah, actually I should be calling this I0 because that's what I actually called it in the diagram, so it wouldn't hurt to put that I0 there and that I0 there. This case is mu 0 I0 times 1 over 2 times 4R0, so this one's going to become 8 lowercase r0, and this one's going to be mu 0 I0 over 8 capital R0, and then all of that will be times k hat, and that is the total magnetic field at the origin due to these 3 arcs and these 1, 2, 3 straight line segments. So hopefully that's a good enough example for you to make some sense of it. Again, you should work on your right-hand rules to make sure you can confirm that the direction due to arc 1 would be into the page, the direction due to arc 2 is into the page, the direction due to arc 3 is out of the page. And thirdly, that the direction of z for a right-handed coordinate system, which is what we're supposed to use when we're dealing with physics specifically, because we have to do a lot of other things to fix our cross products and things of that sort. But in this case, with this X and Y, the Z has to be out of the page. In other words, K hat points out of the page. So I hope that helps. Have a good day. Bye bye.